In this part of the lecture, I'd like to talk about p-n junction dimensionality. So ideally, we want to make a density of states switch. We want to align the density of states in the conduction band with the density of states in the valence band. But what that means is that the density of states is going to be explicitly affected by the dimensionality of the tunneling junction. So that's to say you have a 1D density of states, a 2D density of states, or a 3D density of states. And depending on your dimensionality, your IV curve will have a very different characteristic to it. And so here we can kind of see you could be tunneling in a nanowire, or say in a quantum well, or in a bulk junction. But now we could also ask what happens if we try to confine one side of the junction. Say we're tunneling from a quantum dot to a nanowire. Or if things get more interesting, say tunneling between two quantum dots. Or say we're tunneling between two overlapping quantum wells instead of tunneling across a quantum well. What we'll see is that as we confine in the tunneling direction, we can actually greatly increase the current and get a sharper turn on. If you want to analyze this mathematically, you can go through sort of a Fermi's golden rule type of approach, and you can do that and basically count over all the states on each side of the tunneling junction, and then the trick is trying to find this matrix element. And so sort of here is kind of the initial references, and then there's some more references at the end that explain how to do this. But rather than trying to go through the math, let me just kind of give you an intuition for what's going on. Perhaps the most important thing that comes out is that we find that confinement in the tunneling direction will increase the conductance. So that means that if we put this electron in a quantum well, its current will increase. And the way to understand that is, let's say we have an electron that's confined here. It'll have some confinement energy, and that energy is going to correspond to a velocity. So that means that the greater the confinement, the greater its energy, and the greater its velocity. And so that means that it's going to oscillate back and forth more, it's going to make more attempts to tunnel, and you're going to get a higher current. In addition, when you confine the electron, you're actually just squeezing its wave function more and more. And what that means is that more of the wave function starts to leak out. And sort of the more it leaks out, the larger the wave function overlap you get. So what's useful is if we use that confinement, we can actually increase the current, say 10 to 100 times. And now what I want to do is kind of analyze these tunneling junctions in a bit more detail. And so to do that, I just kind of want to illustrate sort of some ideal density of states switch, so we can kind of focus in on the density of states effect. So let's assume our tunneling probability is roughly constant, and kind of ignore the barrier thickness modulation part of the problem for now. And let's just assume that our bands are just starting to overlap, and that we have this small overlap that's on the order of kT or less. So you can just really look at right when we have our density of states turning on, what is the characteristics of the switch? And then of course, if you try to build a full tunneling transistor, we'll have our gate here that's going to control the overlap. So let's say here we have this overlap, and we have some gate bias on it. Then as we move the gate up, we'll change the overlap. And so I'm just going to focus in on, I'm going to define everything in terms of this overlap and not worry about the gate electrostatics. And so what's amazing is now if you actually go through the analysis, we'll find that these different junctions have very different IV characteristics in terms of that overlap. So for instance, a bulk junction will have more of a quadratic turn on, while say a simple nanowire has a linear turn on. And then now things start to get interesting when we try to confine in the tunneling direction. For instance, if we confine one side of a bulk junction, our turn on goes from quadratic to linear. Or if we go, say, from a quantum dot tunneling into a wire, you have almost a step function turn on. Once the level on the dot overlaps with the levels in the wire, the current just reaches some fixed value. And so I'll explain in a bit more detail, but once we confine both sides of the junction, our turn on becomes even sharper. For instance, if we tunnel from one quantum well to another, we get almost a step function turn on. And this is just because the turn on ends up following the 2D density of states in the quantum well. Or let's say we're tunneling between two nanowires. Our turn on goes as the square root of the voltage actually. And it's just following a 1D density of states. And that's if we're tunneling between two dots, our turn on looks like a delta function. We only get current when the level in each dot aligns. So now kind of here, let me explain kind of where did some of these curves come from. So earlier in the lecture, we saw that if we're tunneling through a simple nanowire, our current is just given by a quantum of conductance times this overlap. And that's just because that's the energy range over which current flows, and the current always flows with a conductance of 2e squared over h, and then times the tunneling probability. And so that means we have essentially a linear turn-on with respect to the overlap. Now we could extend this to 3 dimensions. And the key is that simply that we have to sum over all of the transverse states. So what you could say is that we almost have like a series of modes that are tunneling. And so we can just break our 3-dimensional device up into an array of modes. And so we just have to multiply our 1D quantum of conductance times the number of states. And what we see is that sort of from that 1D quantum of conductance we have that overlap energy, and then our number of transverse states also increases as our overlap increases. So what that means is that our current ends up going as the overlap voltage squared, or we get that quadratic turn-on. And now I actually want to analyze one of the most interesting cases. And this is sort of like that bilayer structure, or a 2D to 2D phase overlap structure. And the idea here is that we're tunneling from one quantum well to another quantum well, but we're confined in the tunneling direction. To understand what's going on in this device, we need to look at conservation of energy and transverse momentum. And so if you look at the EK diagrams, what we see is when the device is off, they don't intersect, and there's no energy at which current can flow. But now when we apply a little bit of bias, we pull this down, and then they intersect, but they only intersect at a single energy, giving us this ring. And so that means that all of our current is flowing at that energy. And we can kind of see how this is different from a bulk junction, because if you look at our total energy, we have sort of our transverse energy, which is fixed by this conservation of transverse momentum. And then we have our energy sort of in the tunneling direction itself, in the z direction. And here it's fixed by the quantum well. But in a bulk junction, it can vary freely. And so that's kind of why we have a little bit of a different characteristic. Alright, so now that we know that our current is flowing at this energy, we just need to ask how many states exist at that energy. And so we look at our 2D density of states. But what's interesting is that the 2D density of states is a constant with energy. So what that means is that it doesn't matter if we have a small amount of overlap or we have a large amount of overlap. The density of states at the tunneling energy will be the same. So what that means is that our conductance is going to be approximately constant. We're going to have an abrupt turn-on, and then it's going to stay constant. And so this is exactly what we want. We want a turn-on that looks like a step function. And so now here I'm comparing all the different dimensionalities. So now what I want to focus in on is sort of this figure in the lower left. So here we have sort of our bulk junction with our quadratic turn-on that's very slow. But then as we saw, the quantum confinement in the tunneling direction can greatly increase the conductance. So we have this red line up here that's almost 100 times higher. And so then you see that this is like a step function, but then you say, well, but wait, there's this dotted region here. What's going on? And that's that we still have sort of our initial turn-on smearing. Either it could be sort of the band-tail density of states or some other various mechanisms. And so we'll have a little bit of a smearing in our initial turn-on. But beyond that, we're going to have this much higher current density, and we'll have this much more abrupt step function. And so that's kind of amazing if you think about it. We're taking this bulk 3D junction, cutting it off, so making it a smaller volume and turning it into quantum wells. And by doing that, we actually get a higher current. And so the same thing happens in lower dimensions as well. Say if you're tunneling across 2 quantum wells, if we then chop it into 2 nanowires, we get a much higher current. And same thing here. If we insert a quantum dot into a nanowire, we can actually get a higher current as well.